Today we're going to talk about simultaneity and clock synchronization. When we're talking about simultaneity in relativity, we're basically asking the question, if two events are simultaneous in one reference frame, in one space-time, are they still going to be simultaneous in other reference frames, in other space-times? And we kind of suspect that because time is no longer absolute, and because it's entangled with space, the answer is going to be no. This can be seen really easily on a space-time diagram. Here we've got three events A, B, and C, and we have a line of simultaneity, a line parallel to the x-axis, and you can see that the three events A, B, and C occur at the same time. However, if we switch to a moving reference frame, now the lines of simultaneity lie along the new x-axis, and you can see that event C occurs before B, which occurs before A. So those three events which are simultaneous in one reference frame are no longer simultaneous in another reference frame. So we looked at simultaneity on a space-time diagram. Let's get a little more concrete now and look at simultaneity on a spaceship. So we have a single event, a flash of light being produced at some point in space-time. We can look at it from the observer on the spaceship's point of view, or that same event from the observer on Earth's point of view. Both observers have to measure the same speed for light. And that's the second postulate. All observers measure same c. For the observer on the spaceship, the walls here are not moving relative to him, and it's an equal distance from the flash to each one of the walls. So naturally the light has to strike the front wall and the back wall at the same time. However, it's quite different for that observer on the Earth, because the spaceship is moving relative to him. So during the time it takes for light to travel towards the back of the train, that wall, which was here, will move forward to here. And the front wall, which was here, will move forward to here. So that relative motion of the spaceship does not affect the speed of light. And the speed of light is not affected by the motion of the spaceship. So the light traveling to the back wall travels a shorter distance. Let's call that d primed. And the light traveling to the front wall travels a longer distance. Let's call that capital D primed. Then the two events are not going to be simultaneous. The event at the back wall is going to occur before the event at the front wall because the back wall is closer. So the flash reaches back wall first, since it's closer. So these two events that were simultaneous in one reference frame are not simultaneous in another reference frame. The IB asked lots of simultaneity questions. So I want to go over a couple with you. Pause the video, try the question, come back for the answer. So let's look at things from Miguel's perspective. He knows that two events occurred at the same point in space-time, and that was the light from A and B reaching him. He also knows that he was exactly in the middle between those two events, so he knows this distance here is the same as this distance here. He knows light was traveling at a speed c across that same distance. And so he concludes that events A and B, those are the original flashes of light, are simultaneous. Okay, let's look at this situation from Carmen's perspective, from Carmen's reference frame. She is going to have to agree that light reaches Miguel simultaneously. Miguel says those two events, the flashes of light reaching him, those two events occurred at the same point in space-time. Well, one point in space-time transforms into one point in another space-time. So Carmen has to agree that light reaches Miguel simultaneously. That's not to say that the two events A and B occurred simultaneously, but that light reached him simultaneously. She also knows that that light was traveling at speed c. But that speed of light is independent of the motion of Miguel. So during the time it took for light to reach Miguel, Miguel would have moved to the right. So Miguel would have started here and then moved to that point. Carmen would also agree that originally, when Miguel was back here, the two events were equal distances on either side of him. So event A and event B were equal distances from where Miguel was originally. So if Carmen agrees here that the light reached simultaneously, she would also say, though, that light was traveling a longer distance from A than it was from B. This is a bigger distance, and this is a smaller distance. Which means Carmen's going to say A must have occurred first because the light had to travel a longer distance from A. Because light traveled a longer distance from A. So be careful here to distinguish between moving objects like Miguel or a train, etc., and events, points in space-time. The points in space-time, they're not moving around. They transform from one reference frame to another, but they remain as points. There's no movement of those points. Here's another example of an IB simultaneity question. Pause the video, try the question, come back with the answer. So Tom is going to see light emerge simultaneously from that single point. But during the time it takes for light to get there, the wall that was here is going to move up. And let's make it move up by 1 unit. So it would move to here, because Tom's seeing Jerry move to the left. And the wall that was right here, it's also going to move to the left. So it will now be here. So Tom sees the light travel all the way to here and to here on the other side. The light hits the mirrors, and that becomes a point event. And Tom's going to see light reflected from that point. So there's light being reflected back. However, during that time, Jerry's been moving as well. So Jerry started out right here. And during that first reflection, he'd move 1 grid to the left. And then during the time it takes for light to travel back to him again, he's going to move another grid. So he's going to be right here for that reflected beam. And light from the left won't have to travel very far, but light from the right will have to travel a long distance. So if you look at the beam that started out going to the left, it's 1, 2, 3, plus 1 units long. And the beam that starts out going to the right, it's 1, 2, 3, 4 units long as well. In this case, 1 plus 3 is equal to 4. So you can see in both cases, light traveled the same distance. So they're going to strike Jerry simultaneously. Now, with a little bit of reasoning, we could have done this question a lot more quickly, because if we go to Jerry's frame, well, of course the two flashes of light have to arrive at Jerry simultaneously, because the two flashes are traveling the same distance, and the mirrors aren't moving relative to Jerry. And if two events occur at the same point in space-time in one reference frame, then they have to occur simultaneously in all reference frames. And therefore, Tom has to see the beams striking Jerry simultaneously. So if two events are simultaneous in one reference frame, why is it that they won't be simultaneous in another reference frame? Well, it comes down to the clocks not being synchronized. Now, what does it mean to synchronize clocks? Well, say we've got two observers separated by some distance. Let's call it L0. Then if they want to synchronize their clocks, say this guy on the right here, he can set his clock to 0 just as he sends a beam of light, which of course would travel at speed c. The time it takes to reach the other observer should be equal to distance over velocity, which would be L naught over c. So as soon as that signal arrives here, that's used to trigger this clock, so it's going to read a time of L naught over c. So now we've got synchronized clocks. But let's imagine some observer moving relative to these other two observers. So from his perspective, he would be standing still, and the pink guys would be moving to the left. The light would still travel at a speed of c between them. However, during the time it takes for the light to reach the other observer, that observer will have moved away. And the basic effect that we're going to get is time dilation. So this guy is going to measure a time equal to gamma times t, a longer amount of time, a dilated amount of time for light to arrive at the other observer. So that means he's going to say that they're not synchronized because the clock wasn't set forward by the right amount. Another way to look at this is if we consider a space-time diagram. If we consider a frame that's at rest, all these clocks should show the same time, because this is the time axis. But if we consider some other moving frame, then the lines of simultaneity, the lines of constant time, would lie parallel to that x-primed axis. So these clocks should show the same time. So if the clocks in one frame are synchronized, they're not going to be synchronized from another frame of reference. Something that we might now ask ourselves is just how out of sync are the clocks going to be in the different inertial reference frames? So let's go back to our common scenario where we've got an observer on a ship or a train and it's going by an observer on the Earth. So we got the ship going by like so. But this time, let's suppose that there's two markers on the Earth, represented by these two triangles. And the observer on the Earth notices that when the front of the train is exactly aligned with that front marker, the back of the train is exactly aligned with that back marker. Now, of course, things are going to look reverse on the train. It'll be the Earth that's moving to the left, and the rocket ship will be still. But what's more is, because the Earth is now moving, the distance between the two markers is going to be contracted in the reference frame of the train. And also this distance of the train, because that's in the reference frame of the Earth, that's going to be a contracted distance as well. That is, the proper length of the train is going to be longer than the contracted length that's measured from the Earth's frame. So from the train, the two events are not going to be synchronous. The Earth will come by moving to the left, and that's going to be event 1 when the front of the train is aligned with the marker. This will be event 2 when the back of the train is aligned with the other marker. So what you want to notice here is that there's some extra distance. So if we want to work out how much the extra time is going to be, that is how out of sync we are, is going to equal that extra distance divided by the relative speed between the two frames. So let's see if we can work out that extra distance. So we'll start by defining a variable. We're going to call this distance here the proper length between those two markers as measured from the Earth. We'll call that L naught. Then of course from the train's reference frame, this distance here would be a contracted length. So it's going to be shorter by a factor of gamma. And this proper length of the train, it's going to be longer than the contracted length here, which we can see is also L naught. It's going to be longer by that factor of gamma. So the proper length of the train is going to be gamma times L naught. So now we can write our expression for that extra time, our difference in synchronization. It's going to be the extra distance gamma L naught minus L naught over gamma divided by the relative speed between the reference frames. So let's see if we can simplify that. So my first step here, I'm going to common factor out gamma times L naught. So on the top I'll get 1 minus 1 over gamma squared. And then we'll have a v out front here as well. What I like about this expression here with the 1 over gamma squared, you'll recall gamma involves a square root. So if I square gamma, I'm going to get rid of the square root. And then if I have a 1 over gamma squared, I'm going to just get the expression 1 minus v over c all squared. So when I substitute this in, I'm going to get gamma L naught all over v times 1 minus 1 minus v over c all squared. 1 minus 1 will cancel out, so we're going to end up with gamma L naught all over v times v squared all over c squared. So our expression for the extra time is going to simplify to gamma L naught times v all over c squared. So let's take this a little bit deeper, the idea of the extra time as seen from the train. So from the train's point of view, we've got the markers on the Earth moving to the left at speed v. We got event 1 when the front of the train crosses the marker on the right. And we've got event 2 when the back of the train crosses the marker on the left. And we know the amount of time it takes for that marker on the left to move from here to here is going to be given by the expression that we just derived. So that extra time is going to equal gamma L naught v all over c squared. So now let's imagine that the viewer on the train can actually see clocks. So he can see a clock at the marker on the left, and he can see a clock at the marker on the right. And then as that extra time ticks off, the marker on the left will move to here. So the clock will be here, and the other clock will have moved to here. That is, these clocks are in the reference frame of the Earth. So the observer on the train is going to see these clocks moving more slowly than his clocks by a factor of gamma. So that extra time for the Earth clocks is going to equal the extra time as seen by the train divided by gamma. It's going to be slowed down by a factor of gamma. So this gamma here will divide out, and we'll get L naught v all over c squared. Now, just to make things a little more concrete, let's say that this came out to be 5 nanoseconds. Let's suppose this clock read 0 nanoseconds. Then this clock here would have to advance to 5 nanoseconds by our definition of this extra time for the Earth clocks. Now, from the Earth, we know that event 1 and 2 occurred at the same time. So the clocks on Earth have to be showing the same values for the same events. So event 2 is at 5 nanoseconds. Event 1 must also show 5 nanoseconds. These two have to be the same. And of course, both clocks here advance by 5 nanoseconds. So this second clock, we call it the chasing clock, would be at 10 nanoseconds. So from the train, he agrees the two clocks are showing the same values. But he says the reason that they're showing the same values is because the front clock and the chasing clock were not synchronized. So let's summarize this result. We had a proper distance between two markers on the Earth in the non-moving reference frame. And we had something moving between those markers with a speed of v. And there was a clock placed right at each marker. Then when our moving observer looks at each clock, if he sees this one, the front clock, reads 0, This back clock is going to read L naught V all over C squared. And we call this second clock here the chasing clock. Let's try to tie down the idea of clock synchronization with a numerical example. So let's say we've got a rocket ship. It's traveling at 0.8 C, which means gamma is going to equal 5/3 or 1.67. And it's going to travel from some planet A to some planet B. The two planets are not moving relative to one another, and the distance between them is 40 light minutes. So let's consider from the planet's reference frame. The time it's going to take for that journey from A to B is going to be, well, distance over velocity. The distance is 40 light minutes, and that's in the frame of the planets, so we don't have to contract that. And the relative velocity is 0.8 c. So when we divide there, we're going to get 50 minutes for the journey. So when the rocket reaches this point, the time on a clock located on planet B would be 50 minutes. And now we'd like to know what would the time on a clock on the spaceship be. We'll call that delta t primed. That's going to equal the distance in the rocket's frame divided by the relative velocity. And the distance in the rocket's frame will be contracted. There will be a length contraction because it's moving relative to the planets. So that's going to be a distance of 40 light minutes divided by gamma, which is 5/3. And then divided by the relative speed, 0.8 c. Work that out and you should get 30 minutes. So the clock on planet B is going to read 50 minutes when the clock on the rocket ship here reads 30 minutes. Okay, let's look at the events now from the ship's perspective. So the ship will not be moving. Event A will be when planet A coincides with the ship. Planet A and planet B will both be moving to the left together. And we're going to have a clock on planet A and a clock on planet B, as well as a clock on the rocket ship. So as the rocket ship passes planet A, we synchronize the clocks to 0. Now, A and B are moving relative to the rocket ship. That means the clocks on planets A and B will not be synchronized in the rocket ship frame. And the clock at B is going to lead, because it's the chasing clock, it's going to lead the clock at A. By how much? By L naught V all over C squared. L naught was that 40 light minutes. C was 0.8 c, and then divide by c squared. You're going to get 32 minutes of lead time. So the clocks are not synchronized. The clock at planet B, according to the ship, is leading by 32 minutes. Now the second event is going to be when planet B coincides with the rocket ship. And planet A would be over here somewhere. They're both moving to the left. We're going to have a clock at B and a clock at A for that event. Now, we said earlier that when the rocket ship reached planet B, its clock would read 30 minutes. So this should be reading 30 minutes. So on the spaceship clock, 30 minutes went by. Of course, the spaceship sees the clocks on the planets running slowly by a factor of gamma. So if I take that 30 minutes and divide it by gamma, 30 divided by 5/3, I get 18 minutes. So if the guy in the rocket ship is seeing the clocks on the planets run slowly, it should see them advance by 18 minutes. So this one at A, it'll advance by 18 minutes. It will read 18 minutes at the end. But this one at B, it's already showing 32. Plus, it advances by this 18 minutes. So it should be reading 50 minutes. And that agrees with the way the planet saw it, 50 minutes. And one more thing to notice. From the point of view of the planets, their clocks show 50 minutes at the end. The clock on the ship shows 30 minutes. So looking from planet to ship, they say your clock runs slow. Looking from the point of view of the ship, 30 minutes went by ship time, but only 18 minutes went by planet time. So once again, they say your clock runs slow. So we have that symmetrical situation where both inertial reference frames see the other's clocks running slowly. And one last thing to point out. This term here for the difference in clock synchronization. It might seem kind of familiar to you. And if I pull up this part of the IB data booklet, you'll notice in the equations for time that we've got Vx over c squared. Of course, x and delta x are just lengths, the same way L naught is. So these terms that are appearing in that equation are really all about clock synchronization. So let's summarize the big ideas from the video. The first key idea was that simultaneity depends on the reference frame. So we began to analyze situations where we'd have an observer on, say, a moving train and an observer on the Earth, and we analyzed to see if events were simultaneous. And the key idea that we had to use was that c was the same independent of movement of everything else. So for this guy on the Earth, it didn't matter that the train and the observer were moving to the right. The speed of light was the same for the observer on Earth. And it was also critical to understand that one space-time point will always transform into one space-time point in another inertial reference frame. So if light comes and strikes a person at one point, those two events are going to be simultaneous in all reference frames. And then lastly, we looked at the amount of clock synchronization. So we would have, say, a moving observer and let's say two planets not moving relative to one another, separated by a distance L naught, and we'd have a clock situated on each planet. Then we said that if the clock on A was reading 0, this chasing clock on planet B would read L naught V all over c squared. In other words, even though the clocks were synchronized in the planet reference frame, they weren't synchronized in the rocket reference frame. And that's all for today, folks. Thank you very much.